final exemplar on these introductory questions then, and the question tells us that the mass of our communication satellite is 550 kilos. We know that the period of the circular orbit is 24 hours, and of course we're going to want to convert that into seconds. That's 24 times 60 minutes in an hour times 60 seconds in a minute, which is 8.64 times 10 to the 4 seconds. I happen to know, which is just a bit sad, but there you go. And the radius of the orbit, just one further over there. Now we have to be careful with the radius of the orbit, because when we're talking about satellites or moons or planets, we might be given the distance above the surface as opposed to the radius of the orbit, and the radius of the orbit is measured from the position of the object to the center of the thing it is orbiting around. So it would be to the center of the Earth in this case, but this is the radius of the orbit, we are told, not the height above the surface of the Earth, and it is given to us in meters, so that's nice and handy. We don't have to convert that. So the first thing we're asked for is the angular speed. So we're looking here at a relationship between omega and the period, because we know the period and we want omega, and it's obvious to look for the connection between the two. So omega is 2 pi over t, which would give us, if we work that out using t in seconds, 7.27, 7.3 times 10 to the minus 5 radians per second. So that's that bit done. And then the second part of the question asks us for the magnitude of the force needed to keep the satellite in the circular orbit and state its direction. So we've worked out omega, we could use t as well, but we've got omega, so we could use that, use mr omega squared, so we've got 550 times 4.2 times 10 to the 7 times omega squared, which was 7.27 times 10 to the minus 5 squared. And that, once I've tidied up the superscripts, gives us 120 newtons. So let's just tidy up those superscripts, and that's the question done.